Okay, let's get started. So today we are actually done with assignment number 2. We're moving on to assignment number 3. Assignment number 2 is about Dino, if you remember. Dino and the Tetrosaurus and the Super Tetrosaurus and all the other people that were inherited from Dino. And all the concepts about inheritance and extending classes. And I started out this lecture talking about that stuff. Assignment number 3, and I'm sort of basing this kind of on the assignments in terms of the order of the concepts that I'm giving you. And assignment number 3, just to preview this a little bit, it's about stacks and queues. And Wednesday we're going to start building this, but before we can start building it, I have to give you the underlying concepts for it. Assignment number 3 deals with what's called abstract classes and interfaces. So an abstract class is sort of an outline or a template for a class, but it really isn't a class. There's no implementation to it. And so the lecture today is going to focus on the concept of abstraction, how to create abstract classes, and then also lecture number 5, which is on interfaces and what's that all about. Because we don't want to necessarily reinvent the wheel every time we want to create something. This assignment here, as we look at it, it's probably going to sound kind of difficult. It really isn't. It's actually pretty easy. And you'll see it Wednesday. I'll put together, I'm not going to do both a stack and a queue. And I'm not going to use the same concept, so I'll put together something similar to this. But what we're going to do is inherit and use an abstract class and an interface from, and you don't necessarily have to use both, and I'll show you that on Wednesday. But so you can kind of build on concepts, the concept of a stack, and then create a stack of something rather than a concept of a queue. And if you're not familiar with the concepts, these are just basic data structures. Just to briefly tell you what this is about. Stacks usually work, it's like a stack of plates in the kitchen cabinet or whatever, or a stack of papers or a stack of anything, where you put the first one goes down first, and then the second one comes down on top of it, and the third one goes on top of the second one. And so it's first in is the last one out, or the last one in is the first one out, which is what this FIO and FIFO and LIFO stands for: first in, first out, last in, first out, if you're not familiar with data concepts, data structures. Basic data structure. In Java, we have stacks and queues already implemented for us. And so we import and we inherit from stacks and queues and all sorts of different built-in structures that are abstract, and then we build a stack of something or a queue of something, and we add the data component to it. The structure is already given to us in terms of enqueuing, dequeuing, popping, pushing, all of the different methods that will go along with that particular concept. So this particular assignment, what we're looking at is a company and people who buy and sell stocks. And so it's not, you don't have to know anything about stocks. So often they buy the same stock for different prices. So say a person owns 1,000 shares of certain stock, such as Checkpoint, which is the name of a stock. You can just say, put in Facebook or something if you want to put it in there. And when did you buy the Facebook stock? Did you get it the first day, the second day, the third day? Because they're all 3 different prices. So normally a person would take all those prices, add them up, divide by something, I don't know, figure out what the average was perhaps. Or you can kind of use a first in, first out approach. How do you know if you sell a stock, what price you bought it at, kind of thing. Depends on what day you bought it at, I guess. So you might have bought a stock in amounts of 1,100 shares over 10 different times with 10 different prices in this particular example. So you're going to write a program that's going to analyze this from an accounting point of view. So you're going to analyze 2 different methods for accounting: first in, first out. So the first stock you bought is the first stock you sold, or the last in, first out, which are both, one's a stack, one's a queue, essentially. You could actually do them both, the same kind of structure, if you wanted to, and just read them differently, and you'd get the same concept. So in terms of FIFO and LIFO, accounting used for determining the cost of the stock. So the information is typically calculated when the stock is sold to determine if a profit or a loss was made, in terms of, did you sell it at more or less than what you paid for it. So in your version of the first in, first out accounting, the price of the commodity is averaged starting with the first purchase of that particular item. So say you sell 250 shares of stock. According to the method, and this is just explaining the concept to you, the purchase price is determined by averaging the price of the first 250 shares So you take an average the price, considering, in fact, you can make up the rules for your program. I don't really care. You're just mimicking the concept. So you could say, I bought them all in one day. Well, then you'd have no queue or no stack, but maybe 2 or 3 different days, and maybe even allotments or something, so you don't have to calculate an average or something. But what you're doing here is say that you sell them, you average the price out. Let's say, for example, in a particular version of last in, first out accounting, the price of the commodity is averaged starting with the last purchase of that particular item instead of the first purchase. Sort of like regular old inventory. So say you sell 250 shares of stocks according to the method. The purchase price is determined by averaging the last 250 shares. So in this particular assignment, you're going to be using a queue for storing the first in, first out. Because if you think about a queue, if you're not familiar with the concept, I explained a stack is sort of like a stack of plates in a cabinet. A queue is sort of like what you get at the bank. The first person who walks in and stands in line is the first person who gets served at the bank. So the queue is first in, first out, which is the first FIFO variation of this concept, which is more fair for, at the bank. If you were the last person that got arrived at the bank and you were the first person that was served, and everybody else at the bank would probably beat you up on the way out. So it's not quite as fair. But if you're running and you're processing information, and let's say, for example, you're organizing plates or something, it might not be economical for you to pull out the first plate from underneath all the rest of them. So certain structures work better in certain environments. Let's just put it that. So you're going to use one that does first in, first out, and you're also going to use one that does last in, first out, which is going to be the stack. So the stack is going to be the last one in is the first one out. So you can use an array if you want in terms of your implementation. For your stack-based implementation, or you can use a linked list if you want. And you're going to go, well, most people in here sitting in here will go, well, I would do an array, right? That would be like the easiest way of implementing this. Believe it or not, the linked list structure is going to be the easiest one, but you don't know that yet because you don't know there's built-in classes in Java that will allow you to just create extensions off of abstract data structure structures. So to implement, you could use a linked list for implementing your queue, and then use some other programming method to accomplish that task or the other task. You can do them both differently. You can do them both the same. Both the stack and the queue must hold records with the following fields: the name of the stock, name of the number of shares for each one of the stocks. So you have multiple fields here. So you could probably put, let's say, a structure inside of a linked list or something if you wanted to. It depends on what you're holding, I guess. Or you could put a class. These could be an object. You can create an object called stock. And I think what I'm going to do for you Wednesday is, and the reason why I'm showing this to you now is you can start thinking about how am I going to implement this thing. And as I'm covering the material that's going to explain how you're going to implement it, I would personally create an object, call it stock or something, or items. And these would be like inventory items you're keeping track of. And you have the name, the number of shares, the purchase price of each one of those items, and put them into an array, perhaps, or maybe put them into a data structure that we could create. So you can assume that the first element of the structure is the security bought first, and the second one is the one that was bought second, and the third one was the one that bought third. You can put them all in the same order. So your program should have the user able to enter information about various different stocks, the amount of shares, and the price. The user can then enter a query based upon a certain number of costs according to the last in, first out, or first in, first out method. And you put up a little menu. When it says, press 1 to enter a new stock, press 2 to find a stock price. You don't really have to do anything for it. Press 1. If 1 is pressed, the user needs to enter a stock symbol and the number of shares and the price of a stock. So basically create an object, put an object into the array or into the structure that you're holding these particular objects in. Or 2, enter the symbol queried and gives you the number of shares in question. So it says, I want Facebook. How many shares of stock do you own? I'll come back and I'll tell you how many, depending upon what object it found. So the implementation described above is done in Java programming language, obviously. Any technique that you want, the overall requirements are described above. Any technique that you want to implement the overall requirements. There's a half a dozen different ways of doing this program, actually. You could do this program with 3 different arrays if you wanted to, holding those three different pieces of information. Those would be parallel. This would be the hardest way of doing it, parallel arrays. You could create simple objects and put them in an array structure. That'd be another way of doing it. Or you can use some of the built-in data structures and create a stack and create a queue, or create one of them and make it both, actually. Hybrid stacking queue. And that's kind of, although it sounds like the most difficult one, it's actually the easiest one. But you can dwell on the description of this particular assignment. It's the theme that we're going to be working with for the next couple of lectures. So, any questions on the initial assignment? Again, Wednesday I'll be giving you I'll just like Dino, I'm going to start through and start building it for you. But I didn't actually finish all of Dino. There's still some left you guys can do. So came pretty close though to finishing Dino. Okay, last time we were talking about inheritance, and this is why it says extending classes. So I'm going to kind of skip through what I've already covered and get to the point where it's brand new. There we go, make this so it looks good. Talked about classes and subclasses if you weren't here. We looked at the person and student that extends person. That means student is the is the subclass, and person is the superclass. Super's on top, sub's below. A super can be a sub can be a super, vice versa in the hierarchy. Everybody comes from object. Everybody's inherited from object, which means everyone can go back to object. Talked about upcasting. Upcasting is when we take a student as an example and we take an employee as an example that are both people, and we go up the hierarchy back up to person so that they're both equal. So we can all store them in the same array or do something equivalent to all instances of person. We looked at the concept of extending classes and including fields and including methods that were included in the base class. So our inherited classes have everything that's included, so we have two sets. Well, in this particular case we have two sets, because object doesn't really come with anything outside of basic functionality. But student has all of persons as well as all of students, methods and data members. Constructors, and the concept of the constructors, we spent a lot of time on that one actually. The concept of super, which we've seen so far in this, so hopefully you're familiar with that at this point. And the order in which the constructors fire. So we know that the constructors start at object level and go all the way backwards, reverse order. So when we make a Trechosaurus or a super tetra, that's a Dino. Dino's constructor fires first, and then tetra, then super tetra, and then whatever is above tetra. So the three phases of the object construction: and invoking the superclasses constructor, initializing the fields, initializing the blocks that might exist if we have blocks in there, then executing the body of the constructor of the current object. So we looked at that. Skipped that example because that's kind of confusing and showed you Dinos instead. Talked about the concept of overloading and overwriting. Overwriting removes. Doesn't really remove it, actually, which is kind of different than in C++. Actually, someone reminded me of that, actually, and I sort of thought about it and went, yeah, he's right. In C++, you really do overwrite it. In Java, you don't really overwrite, you hide it. So it's hidden. So what does that mean? When you make a subclass of a superclass, and you put in the same data member or the same member function, you repeat something identically. So same name, if we're talking about a function, same name, and same number of parameters in the same order, it's identical. You've hidden the one in the base class because you can't access it anymore, which means you've overridden the behavior, which means every time that method's going to be called from that object, it's going to take the last one that was created. If you upcast it though, and you take that object and you turn it back into the previous object, you've got that current method. You got the old method, because the current object, which is the previous one, it's the lower superclass object, didn't get overridden at that point. So that's hidden if you think about it versus overwriting it completely. So anyway, overwriting is removing the functionality and replacing it with something new. Overloading is complementing it. We overload constructors all the time when we create new constructors that take on different number of parameters. in an inherited class. When we extend one class from another, we can call the previous classes constructors. We can also create, and we should create, our own constructors. We need to create a constructor if we're going to inherit. If we have an inherited class from a base class that doesn't have a constructor, we're going to get a compiler error. We need a default constructor at least, because something has to trigger. Because when we make that instance of that object, the compiler is looking for something. So we talked about overriding and overloading in terms of the concept. Accessibility, we talked about the private package and protected public methods that are accessible. And I still haven't fixed the typo on the bottom of the screen. It's no big deal. So let's see, we got as far as maybe abstract classes. I just talked about hiding fields a minute ago. So the field can't be overridden, they're only hidden, which means, well, what's a field? It's a data member. So if I said color, and I had color in, let's say it was I don't know, hair color for a person, and then we created a student who also had hair color, it's hidden, is what that's basically pertaining to, especially if we create and use the same name. So in practice, if you don't want to hide fields and you don't want to hide methods or override things, then just use different naming. So you have complemented it and you've overloaded it without overriding it. So talked about the concept of polymorphism, and I said that comes in many different forms. In fact, we've seen 2 of them already. So an object that can have multiple forms, either is declared as a class type or as a subclass of it, is polymorphism. So that concept of upcasting, taking a person and changing them back into a student, is polymorphism in one form. The other one we've seen so far is with overloading. So we can take and we can have, print out an integer, print out a float, print out a double or something. And it's the same method, it's called the same time, we use it the same way, but it reacts differently depending upon the input that we give it. And then we create polymorphic constructors when we overload the constructor to add, a name plus a student ID for a student object instead of just a name and an age or something like that. And an object of an extended class can be used whenever the original class is used as well, because of that is-a relationship I talked about also last time or the time before, where a person is a student or a student is a person if they're both of the same object type. So the question came into play, in fact we covered this question last time as well, invoking methods of different reference types of the actual class of the object decides which implementation is going to be used in terms of, if you do have multiple implementations and multiple member functions or data, which one's going to be used, which is the focus of that question. And in terms of the declared type, well, it depends on what, if a student is a student, then it's going to react differently than if the student is a person. So the person object is going to respond differently, it's going to have different data than the person. Person is going to be different than the student, vice versa. I think I brought up some weird bar example as well about drinking beer in a bar as a teacher. So if you remember that example, that's basically where we stopped, I believe, last time. No, actually we got here too. Strongly typed language. So we know that we can set null object references. It's compatible with all of the different reference types. Any object can be null. Null means it's not set. So in terms of compatibility, you can assign the value of expressions to variables. They must be of the same type in order for it to work. So it must be of the same type or a subtype of the declared type. So a student, going back to the person-student example, a student is equivalent in terms of type to a person because a student's also a person. So we have a little bit more flexibility when it comes to object orientation because of that object is a relationship in terms of types and comparing types. And we talked about, and I got this far as well, widening and narrowing conversions, taking a student and turning him back into a person, which is widening it, versus taking a person and turning it into a student, which is narrowing, which is upside down for me, so I always have to think of it weird. Let's see, we actually looked at these examples in terms of how we actually do, and this is an example of what I'd call the upcasting. This is just a cast though, however, because we're taking the object and we're taking string that was a string, and we're saying, well, make it into an object. which is going to be equivalent to any other object out there, actually. In fact, every object is equivalent to every other object out there because they're all objects, because they're all inherited from object. Can't do this with built-in data types, however, but you can do this with string because string is an object type. Integers, floats, and stuff like that aren't really objects. They're primitive data types that are inherited from C. That made it into C++, that not really object types. However, everything, or mostly 90% of everything in the language is an object. So you can mix and match it this way. We looked at this already as well, but we can't take object and turn it into a double. It just doesn't contain an object double inside of it. So, and I believe we kind of looked through this example as well. Kind of skip through it because I don't really like it because it's kind of confusing. But it's basically taking people and person and students and putting them into an array, and then trying to run methods on each one of them, not knowing which one each one of them is, and coming up with issues with, well, wait a minute, the array index is not really the right person. Because once you take objects as an example, take a bunch of objects, cast them all as objects, put them in an array. When you pull it out of the array, how are you going to know what it is? Is it a student or a person? Well, this is how you know. You check for instance of, and the key word is instance of. So you say, if the object is an instance of string, then we can treat it like a string. So what you're going to end up doing eventually, in fact, you can probably do this with your stock program. As you can say, put all the stocks in an array together and say, well, is this a Facebook stock? Is this an eBay stock? Is this a this stock? And then you can say, is it an instance of that? Is it an instance of this? And then you can tell what it is, but it's all stock. So you can all stick it into the same array for purposes of first in, first out, last in, last out, whatever. And this is the syntax you use, instance of the test to see what is this object. After we casted it to object or something, or made it into something. And that's true for object in this particular case, but it's also true for other types of objects. As an example, we can test to see if it's a student, or is it a person, which is a type of object. This is where we stopped. Abstract classes and methods. So, abstract classes are classes that don't exist. They're abstract. You can't make an instance of an object of an abstract class. It doesn't exist. How can you make an instance of it? So, how do you make an abstract class? Well, any class that has an abstract method in it is automatically an abstract class. But we use the keyword abstract, and here it is here. I'll zoom in a little bit so you can sort of see the syntax. Just like regular old class, but instead of putting public here, actually, you can leave out public. And then by default, all classes are public. But instead of putting, in fact, you could put public abstract class. Well, no, in this particular case, it's abstract class. We don't need an access method because we can't access it. We can't do anything with it because it's abstract. What does abstract mean? It means it doesn't exist. Well, okay, by definition, abstract, some methods are only declared, but no concrete implementation is provided. So they need to be implemented by the extended class, which means the class is made for inheritance. So in a particular sense, person, in our example, doesn't necessarily need to be a full object. It could be an abstract class, and then we can create employee and we can create student from it. In this particular case, person would be the abstract object. What does that mean? Well, when we build the objects, if we can still cast it to a person because it's still a person object. It still comes from the sys. It doesn't change the hierarchy at all. It doesn't change the is a relationship either. But it cuts down on the number of work that we have to do. If we know we're going to override something, we're going to override it, we're going to provide implementation for something, why build it originally? So, if you think of the concept of, let's talk about shapes for a second because this lends itself well to a good example. If we have the concept of a shape, I'd make shape abstract and say maybe shape has a number of walls, maybe it has a diameter, I don't know, maybe, these are basically methods or data that would be stored for the concept of the shape. What kind of shapes? We can have a triangle, a rectangle, a square. We can have all sorts of different shapes that could be derived from extending this concept of the shape. What we'd put in the shape is the basic concept of what it is we were trying to achieve. Just low level, basic, number of sides, number of legs, If we were a person in this example, it would be number of legs 2, number of eyes 2, number of hands 2. You know, the basic, every employee, every student is going to have 2 arms, 2 legs, 2 hands. So there's nothing really much to do with that. But it doesn't really extend itself too well for an example, so let's go back to shape for a second. What about if we had a method in there and we called it an abstract method called area? Why put in a definition for area in shape when the area of a square is going to be different than the area of a circle? And they're both shapes that are going to be derived from shape. So if we could accidentally not implement area and we implemented it without using abstraction, we created, okay, area of our basic shape is length times width. Oh, okay. And then we created a circle. And we said, okay, circle dot area. We get the wrong area for a circle, which lends itself to errors. This is if we didn't use the concept of abstraction. We just built it, and we put the implementation in there. Oh, we just left it blank, and it just printed out, hey, this is the area. Not going to be very functional. So a lot of people would sometimes not use the keyword abstract and just leave it empty. Just print out, put your area here, and then it requires the programmer to implement it. And so what are they going to implement? Well, then they have to worry about overwriting or overloading. Then they have to go back to the original area and say, well, what was in there? How many parameters did it take? Oh, it took length and width. Okay, so it looks like I have to overload this, you know. And it requires too much thinking. So what you're doing is, if you're using an abstract technique, you're not going to implement anything at all. You're going to put the concept in there, you're going to call it area, and then you're going to require the person who extends from this class to implement area. Because if they don't implement area, they're going to get an error message. Compiler won't let them continue, which means you have to implement area. So you're setting rules, you're setting requirements, making up, you know, stuff so that in order for a class to be extended from this particular class, you have to implement this method, you have to implement that method. You get this all the time. All of the built-in classes have this. Because what ends up happening is they know in order for the functionality to be complete, you're going to want to have to implement this method, this method, and this method. We see this in the Android class actually because all of the Android implementations require, you know, on-click listeners or on-click events and stuff. When you inherit a class, you go, well, we'll make this a listener. Okay, then all of a sudden you get, oh, do you want me to include automatically this method body, that method body, because you need to implement it. And it builds in the little templates for you. That's what it's doing. It's an abstract class that you inherited from. So here we have an abstract class called person here. And I'm going to talk about protected in a few minutes. I believe I've talked about protected yet. But protected basically means anybody who's it's private to everybody except for people who inherit. So you're not going to have anything private inside of a abstract class because you haven't implemented anything. There's no way of even using this abstract class. So there's no secret. So everything's going to be protected instead of private because we're meant to inherit it. So in person here we have the same as before. We have string name, but now we have public abstract string get description. So it's a method called get description that's going to give us a description of the name. Notice it sort of looks like a function prototype actually. It's got a semicolon at the end of the line. If you're familiar with C or C++, it's exactly like a function prototype actually that you'd put at the top of a program and then you'd put the function body implementation further down, which is a function prototype in C or C++ is an abstract function declaration that says, hey, I'm going to use this somewhere. And if you don't implement it, you'll get an error message. But you can use it before it's implemented. And then lo and behold, eventually the compiler finds the implementation and uses it. Same concept here. You're going to put it here, but it's not going to be implemented until further down the road. Some inherited class from this class is going to implement it. And so the compiler is going to find it eventually further down the road. So now we have the same as before, and this is the only difference. We put the keyword abstract on here. So now we have class student extends public, extends person. Can't think today. We have private. We can have private methods, and we can have private data in this particular class because this one you can make an instance of this particular object. Just remember, you can't make any instances of any abstract objects. They don't exist. But now we're going to extend, and this is what we learned last time. We can take and create a student, and we can, superclass person. We have private string major, so students have majors. Down here we have class employee. Employee extends person, and we're going to add. We can add a private float salary. So students don't normally. It's the other way around. You don't usually have to. You have to pay to take classes. You don't usually get paid to take classes, unless you're a student employee, perhaps. Then you work, you get paid, and you take classes. They pay you to take classes. I don't know how that works, but anyway. Long story short, we have two different variables that are set for two different types of data that needs to be held by two different types of objects that are both extended from person. And now we have we're going to return in here our get description. So this is the abstract method here. And the abstract method doesn't have an opening and closing body. It just has a semicolon at the end of it, which is interesting. And then this is sort of like the .h file, actually, of a C or C++. If you're familiar with that. Some people who have taken C can kind of relate sometimes to that. So what do we have here? We have get description, an employee with salary such and such. Here we have a student with major such and such, because we have the major in here, we have the salary in here. So we've created two instances of, we've created two new classes, employee and student, that are both extended from person. And person is abstract. The reason why person is abstract is because we have an abstract method in here. So each method which has no implementation in the abstract class must be declared as abstract, otherwise you'll get an error. You'll get a compiler error. So abstract means you're not going to give it a function body. You're not going to give it anything. Any class with an abstract method must be declared as abstract. So as soon as you have one abstract method in that class, it's an abstract class. So you're not going to put an abstract method in any ordinary class that you're going to create. Otherwise, you can never make an instance of that class. You're going to always have to extend from that class. So if you ever think you're going to make an instance of that class, as an example, Dino, I made a lot of Dinos, but if he were abstract, I wouldn't be able to. I'd have to make Tetrasauruses and all the rest of them. No Dinos. So when you extend an abstract class, you have two situations that exist. You can leave some or all of the abstract methods undefined. So let's say you're going to make a class, you're going to extend another class that's abstract, but you don't want to implement anything yet. You're going to take and create a shape that's going to turn into another shape through another extension, and you want to say the area for the further one down the road or something. You can just basically bypass it, skip a level. Somewhere along the lines, the class that gets made into an instance of an object must have the implementation, but it doesn't have to exist in the class that immediately extends from it, if that makes sense. You can define concrete implementation for all of the inherited abstract methods if you want to, and then the subclass is no longer abstract. Once you've implemented it, the subclass turns into a regular old object. So we can still make, in this particular example here, we can still make a person. We can still make an employee and get a person object out of that, because employee is going to implement, and it has implemented, the one and only abstract method that was in person. Both employee and student both implemented that method, so it's no longer abstract. There's a method body for it, which means we can take employee and student and upcast it back to person, and we can make a person object out of that. Actually, it works because we've implemented it. If we haven't implemented it yet, then we're going to get really weird behavior. We're going to get really odd kind of stuff coming out of that. An object of an abstract class cannot be created. That means I can't create a person. I have to create a student or an employee, because there's missing implementation. And note the declaration object variable of an abstract class is still allowed, but such a variable can only reference an object of the non-abstract class. An example on the bottom might throw you around for a while. Person P is equal to new student. So remember when I when I was doing the upcast example, this is a reference object. So person P is an object type P, but before I said, well, you can't make an instance of an abstract class, and how can you say person P? If I said new person here, the compiler would give me an error message. So this is okay because student has implemented person. So I can create a student that includes a person and reference that as a person. But I can't create a new person because person's abstract. So if I said person P is equal to new person, no, sorry, can't do that. Alright, but person P is equal to new student. Yeah, because student has person in it. So it's type compatible. Every student is a person. So it's apples and apples. And student has implemented person completely. Now if student hasn't implemented person and I still have abstract methods, compiler is going to go, wait a minute, sorry, can't make an instance of an abstract class. And I believe the message says something like that. It says, actually it probably comes back and says person is abstract. And you're like, okay, so what are you talking about? You didn't implement it yet. Okay. That's kind of an important concept to remember, because then this gives you light, or sheds some light on the concept of the is-a relationship in terms of what's going on with abstraction. So feel free to stop me if you have questions. Yeah? You have a question.
So can you make a class abstract when you have the methods unimplemented?
Unimplemented. That's the purpose. You're making, if you have one, just takes as one method that's not implemented, and you put abstracts, you put this method in this class, any class, then the entire class has to be abstract. You can have methods that are implemented. You can take and implement the whole thing, except for one method.
So an abstract class can have only the unimplemented methods?
Yep. Which is people get so confused on abstraction and abstract classes, but that's all it is. It's just a class that doesn't have any, at least one of the methods isn't implemented. It makes it an abstract class. I could actually take this class, take that one implement. In fact, people do this, and I don't understand why, because they're going to inherit from it anyway. They'll make the class, they'll take it and not make it abstract anymore, and then they'll implement that method. Just say, print something out to the screen or something. It's something stupid. It doesn't really do anything, but it's implemented. It's no longer abstract. Then they can make an instance of it. It's because they don't know this part. They're trying to make a person, but they don't know they can make it through student. Because student has implemented person's abstract methods. So it's no longer person for student is no longer abstract. But person on its own is abstract. And the same thing true for the employee that we created here. So an employee that includes a person is no longer abstract. In fact, the class that we inherited from, we didn't use the keyword abstract. We can make an abstract class from an abstract class if we want to. Which means if I put the keyword abstract here and I added stuff to person but I didn't implement it, or actually let me rephrase that, to student. Let's say, for example, I want to create person, student, and then I want grad student, undergrad student, and I don't know, some other student, or just do two, grad and undergrad. So then I could make student abstract, and then by the time I made grad student would include the implementation for the student that was missing, and also the implementation for the person that was missing from the abstract. Why would I want to do that? Well, maybe grad students have different majors, they have different classes, they have different campuses or something. There's something totally different from undergrad students, perhaps. Why implement something now when you're going to have to overwrite it later? So abstract classes eliminate the need to override behavior. Instead, you're overloading, because technically you don't want to override stuff, because why did I do this when somebody else is going to... It's like if I go and take a broom and I sweep out an area, and then someone comes in after me with another broom and sweeps out the area. Like, what was a waste of my time? Why do I want to do that? It's because, same thing with the objects. Why declare information about the object when you're not going to use it, ever? So, abstract classes was a way of making it so that, not only are you not wasting time in your implementation, you're also letting the world know you're not wasting time. Because if you have an abstract class and you have a method in there, you want the class that inherits from it to implement that method. And if they don't implement it, their class can't exist. You're going to compiler error. So you're enforcing rules. You're saving time, enforcing rules, and creating a foundational structure. Because when we talk about object orientation as a concept, we start with broad and we go to specifications. They're specific. We go more specific. So the higher you get up into the hierarchy, the more, or the lower, depending upon which way you look at it, the further down you go in the hierarchy for the subclass, you have specifications that are more specific, specialized, that are different, but they're enhanced. So a person that turned into a student, that turned into a grad student, that turned into a CS grad student, that turned into a, I don't know, a major concentration of the CS program of the grad student or something. You're getting more specific, so that's the way the hierarchy is supposed to grow. And so you can go back to different levels in the hierarchy, depending upon what level you're at. So what we're going to do with the abstract classes that are associated with data structures is we have a linked list, and we have different types of linked lists that build on top of linked lists. Then we have different types of queues as an example for the first in, first out, and the last in, last out, or different configurations that we can do, which are more specializations. So you can pick a class anywhere you want in the hierarchy, subclass from it by using the keyword extends, and then make your own custom behavior that comes out of that, essentially. So that was a good question. Any other questions, actually? This is like the heart of inheritance, so this is the hardest part in the entire course as well. It gets easier after this. If you can master, well, interfaces, inheritance, and abstract classes, I'm going to talk about interfaces next. If you can master after today, which is like almost the halfway point in this course, actually, then you've got everything down, actually. You're an expert object-oriented programmer. So let's see, we covered this slide already. Protected. As I said before, it allows subclass methods to access the superclass fields because they're defined as protected. But they're private to everybody else. They cannot be used in main. Well, they can't be used in main anyway. You can use protected anywhere you want. It doesn't have to be an abstract class. You can put protected methods, protected data members in any class. Makes it private to main. But if you're extending a class from that class, it makes it public to that class. So it's protected. So just another one. So making methods protective makes more sense if the subclass can be trusted. Yeah. To use the method correctly, but other classes can't. So unless you're subclassed from that class, otherwise other classes can't see it, can't use it. So what protected really means precisely a protected method is accessible within the class itself, just like private, actually. Within the code in the same package, just like private. It can also be accessed from the class from an object reference that are not of or at least the same type of the class. That is a reference of the class's type or one of its subclasses. Right, to simplify the whole thing, it's private to everybody except for public for inherited classes, which is where protected comes into place. So, and here's your little example. Here we have public class employee with protected date. And this is a date object that we're using in here, hire date. And we have manager, which extends employee. And in here this is okay that the class is a manager because it extends employee. To print the hire date, we're going to take employee and we're going to send it in. We're going to print out p.hiredate because manager extends employee. But this is wrong. The class is manager, but the object reference is of type employee, but not manager. And then you can't go the other way around. So as long as it's a subclass of the superclass, you can access it because it belongs in the same hierarchy. If it's at the same level, no, it's protected, which means it's private unless you're inherited. So just remember, public for inherited or accessible by inheritance. So, object, the ultimate subclass. Talked about object already. Actually, everything inherits from object. Here's some interesting things, though. We can actually make clones of objects. We can make object assignments from one object to another object as well. This is just a little tidbit information for you. We've pretty much covered abstraction already. The object class is the ultimate ancestor. Every class in Java extends from object without mention. So we don't have to say, in other languages like Objective-C, you have to say, NS object. Okay, probably just leave it out. But you have to explicitly say object on it when you create a new class. So utility methods. So because we have objects, and as before I said, well, an object doesn't really exist. I mean, object exists, but it doesn't really have any much functionality to it. This is about all the functionality it has to it. We can say, is it equal? And these are built-in methods that come inherited automatically. Because we created an object, automatically, all objects have these particular methods that we can run on them. And we inherited them from object without actually having to say anything, without having to extend object. If we were another language like Objective-C, as I mentioned before, we don't have to inherit from object. We can inherit from other things, other types of objects. Java, we only have one object. So if we only have one object, we only have one choice. That's why they pulled it out and said you don't have to say extends object, extends object, extends every time you create a class, because we only have one object. Everything's going to extend object. If we extend the language, and this might happen in the future actually, let's say you're developing on a different platform, you're going to extend something to another type of object. Who knows? Maybe we'll be extending NS object and JY object and this object and that object. Extension of Python or something. We'll have different types of objects. So then you might end up having to specify it. But for right now, no specification. There never has been in the history of Java. So what do we get from object when we automatically extend from it? Well, we get equals, returns whether two object references have the same value. Is one equal to the other? We get the hash code, returns the hash code of the object, which is derived from the object's memory. Think of it more of a pointer to the object. So equals object should return identical hash codes. So it's not really a pointer because we never have two pointers that are identical, but the hash code to it is sort of the equivalent in terms of the record keeping. So if two objects are really equal, they should have the same hash code. So clones returns a clone of the object, just like multiplicity, a clone. Take person, make another person, make another person, make another, all the same person, same hash codes, they're all equal. They're just multiple of them instead of just one. So cloning is possible in the object-oriented world, not in the real world yet, but soon. Get class returns the run expression of the object's class with a class object. Get the class run expression. Finalize the object during garbage collection. What does that mean? It just means clean it up, get rid of it. Garbage collection I'll talk about a little bit later on in the course. Actually, we don't have to worry about garbage. We never have to worry about garbage collection. There's no delete in Java either. We can go new all we want. The JVM does all of our collection. Finalize just says send it out there, let it get collected. We're done with it. To string returns a string representation of the object, something that we can print out, we can use for something else. So, design hints for inheritance. Some concluding thoughts about inheritance. Place common operations and fields in the superclass. So person, if everybody's got a name, an age, a height, a weight, I don't know what else we're going to have, but 4 arms, 2 arms, 4 legs, I don't know how many legs, but if we all have like the same number of something, put it in the superclass. And because what you're trying to do is not have to kind of reinvent the wheel as you go down. If not everybody's going to have it, don't put it in the superclass, which just makes it abstract. If you have stuff that's going to be determined later on, make the base class abstract. And then just put a placeholder that says area, weight. I don't know, maybe some objects are going to have different characteristics that are going to attribute to certain different things. Try not to use protected fields. Protected fields can cause confusions and problems, especially when you don't inherit. So if you know it's going to be private, make it private. So if you make the data members private and the member functions public, you're in good shape in terms of the exposure. If there's something inside of the class that's functionality for the class and it's a method, make it private. You can have private methods as well. If you know you're going to inherit from it, and you know you're going to use it in the inherited class, then you make it protected instead of private. Never make it public. So, unless it's really supposed to be public. Use inheritance to model an is-a relationship, so that every single class is a instance of the other class. So a shape, everybody's a shape, everybody, a student, an employee, they're all people, persons. Don't use inheritance unless all inherited methods make sense. Otherwise you get really weird behavior that happens. You get birds that act like planes because you're inherited from a class, or you made your hierarchy so it didn't make any logical sense or something. Or kangaroos that act like birds or something weird. Don't change the expected behavior when you override a method. If you have something that says print and you change it so it scans, or it deletes, or it does something else, then you've really messed up the entire concept of printing, and then you're going to have problems further down the road. Use polymorphism, not type information. So if X is of type 1, action 1X, else, this is a bad. So do action 1 and action 2 represents a common concept. If they do, it makes more sense for the concept and a method of a common superclass or interface for both types. And then you can simply call X.action. And then the action will be determined inside of the method. So this is a lot of work that's done in main. As I was going back from day one, I hope I mentioned that the classes should do all the work, the objects should do all the work. Main should be very small. The driver program is very small. If this were out here and you were doing a type information, you can have a check on a type. You could just make a polymorphic method out of it. So you just ran an action. It doesn't matter what it is. It would actually react properly. And then it's only created once. You just run the method on each one of the objects, and you're not reinventing the wheel every time, and it's less work. So this is just like this concept here, where you've got an abstract class, but people are afraid, oh, we can't make an instance of it. We can't use person. And then they don't know this. They don't know that, oh yeah, you can. As soon as you make an instance of an object that contains the abstract class, you have the object contains that abstract. It's a real object person, which means you can assign it to a reference of that same type, that same object type. Those people that don't do that, that's common misconception. People don't know that they can do that. This is the other one. They don't know that. Make it polymorphic. Make the method polymorphic. So you run the method once. Doesn't matter what object it is. You just run the method. Same method on the same object, on different objects, and it works, like print or something. Instead, you'll see, if this, then do this. If this, then do that. If this, and you see a bunch of confusing spaghetti code leading to logical errors eventually, when it's really unnecessary if you just make the methods polymorphic so it responds how it's supposed to. So, but you won't do that until you've gotten some experience and you figured out, oh, how do I make this simpler? And that's where you can kind of, tweak things further down the road. So. All right, second half for today. I'm getting through this. See, I'm going to get through the lecture stuff Wednesday for the Java class. We're going to be going through abstract, and I'm going to bring up data types, the abstract data types. So we'll be making stacks and queues and stuff. Because I have to give you interfaces first too. Otherwise the code examples aren't going to make sense. So abstraction and interfaces are often used together to accomplish similar tasks. What's an interface? An interface is a way to describe what classes should do without specifying how they should do it. It's not a class, but a set of requirements for classes that you want to conform to the interface. You're like, well, what in the world then is an abstract class? Well, here's the trick in inheritance. It's a single line inheritance. You abstract class and you extend from the abstract class. And you can implement as many interfaces as you want. So interfaces provide, this is the nutshell explanation of the two concepts. Interfaces provide multiple class inheritance, multiple line inheritance in a single line language. And it's actually doing the same. Interfaces and abstract classes are very similar in terms of the concept, but you can only extend one class at a time. Implement as many interfaces as you want. And so you use you use two different keywords. Extends, inherits one class from another. Implements an interface. What is an interface? It's an abstract class in concept, but it's built a little bit differently and contains even less information. It's a blueprint. So when we look at Wednesday, when I look at the examples, we'll be extending and then implementing, because we'll implement the concept of a stack, implement the concept of a queue with a template that's already given to us. And the template is the interface that we're implementing. So public interface comparable. This is not the keyword class. So we use the word interface in replacement of the word class. Because we're not creating a class, we're creating an interface. Abstract classes are classes. That's why you can take and extend one class from an abstract class, because you're building a hierarchy of classes. And eventually, as we saw before, that abstract class turns into an object once it's implemented further down the hierarchy. Interfaces never turn into objects, and they are never instantiated as objects, but they're implemented. The functionality is implemented. So let's take a little bit further look at this. Public interface comparable looks like a class, but the keyword class would go here instead if this were a class. There's no abstract. It's not abstract. It's an interface we're creating. It's public because we need to extend from it. Makes absolutely no sense to have a private interface. What are you going to do with it? It's kind of like saying, hey, I built this model, but you can't look at it. Okay, what are you going to do with it? Throw it away? Keep it? It's a trade secret. Hold on to it. So let's see, this requires that any class that's implementing the comparable interface contain a compare to. It has one method in here. It doesn't have any data in here. It has a method. We can put data in, we'll see that in a few minutes. But looking at a method here, and the method says integer type is integer compare to object. So it compares one object to another object, which is what this interface comparable is doing. So if we implement this interface and we don't implement this compare to, we get an error message. So it's the same thing happens with an abstract class. We extend an abstract class and we don't implement an abstract method, we'll get a compiler will come back, hey, did you mean not to do that? Or if we don't tell it we're going to do it later, did you mean you weren't going to implement it? Then you're going to get, you're going to essentially, why did you inherit from me if we're not going to implement something? So what do we have here? It contains a compare to method. The method must take an object parameter and return an integer in this particular case, which is what this method is supposed to do. So interface declarations. The declaration consists of the keyword interface, as we've seen here, public interface, and its name and the members that are associated with it. So similar to classes, interfaces have three types of members associated with it: fields or constants, data members, member functions, and nested classes and interfaces. Common to see interfaces nested inside of interfaces. We didn't see. I made an instance of dinosaurs when Dino made babies, or one of them made dinosaurs. Made instances of objects inside of one of the dinosaur objects. We can actually implement classes, subclass, inside of the class, and that instance of the object that's subclassed belongs to that class. So hardly ever done. Why would you want to do that? You'd probably pull it out, and that way you can use it in multiple different classes and make instances of the object all over the place. But sometimes it's particular to some sort of behavior or some sort of functionality that exists inside of that class, which you get more with interfaces. So we have nested classes and interfaces inside of interfaces. So interface member constants. So an interface can define named constants, which are public, static, and final, automatically actually. These modifiers are omitted by convention because they're automatic. Interfaces never contain instance fields. You can't create an instance of an object type interface because it doesn't exist. The same reason why you can't make an instance of an abstract class either. But you can make an instance of a class that implements an interface. If you make an instance of a class that implements an interface, it can include a named constant, such as one of these down here, silent, terse, normal. It's never going to set the value. So it's always final. It's always static because it's for the interface level, which is sort of the class level. Not an instant. It's not an instance variable. You put the instance variables in the class that you create that implement the interface. So it's like tongue twister today. So this will all make sense eventually once you get familiar with the concept of the interface. And if you can just kind of get the concept down, you'll be successful. When we say we want to interface something, we're just giving it a template of behavior. And in the template of behavior that we're going to give it, we might need something like pi or something like silence or terse or normal, something that's going to be used inside of it in terms of the implementation. If we're doing that, we're going to create named constants. So all of the named constants must be initialized. So we have to say that silence is 0, terse is 1, normal is 2, verbose is 3, as an example. We're just setting some integer values for an interface called verbose in terms of that. So in here we have a method that says set verbosity interface integer level, and it's going to be one of these levels. And then we're going to have something that says maybe get verbosity. So we have a set and a get method. These are not implemented. They look just like abstract classes actually. They look like function prototypes. They have a semicolon at the end. There's no method bodies in an interface. Methods for interface members. So they are implicitly abstract. So you don't have to put the keyword abstract in there, but they are abstract. So you admit it by convention. So every method declaration consists of an abstract header and a semicolon at the end. They are implicitly public. They have to be public. If they're private, you can't do anything with them. You have to implement this somewhere else, so they have to be exposed elsewhere. They're omitted so public is also admitted. So all of the things that are naturally inherent in the concept is taken out. You don't have to write. You can write it in there if you want. You don't have to. No other types of access modifiers are allowed. So they can't be final nor static, actually, either. These are for the methods. You can't have a static, because you'll never make an instance of the interface. How are you going to run a static method from it? It won't work. It's like, if you remember the static concept, it's if you have a static method inside of a class, you can run it from the class without the instances. But you can't, interfaces aren't classes, so they don't exist in terms of the hierarchy. They don't exist in terms of the object structure. Modifiers for interfaces itself. So the interface itself, an interface can have different modifiers. It can be public, or it can be abstract. If you put an abstract method implementation inside of an interface, the interface has to be abstract. Same concept as the abstract class. They're not a class, but it's the same concept. So interfaces that are, all interfaces are implicitly abstract because their concept is that you're creating an abstract interface because you have methods in there that are just templates that aren't, there's no bodies in there. So you omit by convention, you omit the word abstract, so you don't have to put that in there either. So you don't ever have to use the word abstract, you don't have to use public, private, anything. So they're a little easier to create, yet when you look at them, they're a little confusing. As an example, let's go back and revisit this one for a second. This might be a little confusing. If we put the abstract, maybe, if we put that in there, I don't know. We put some modifiers. There's no modifiers in here. There's nothing, or there's no accessors, nothing. To implement interfaces in a class. Okay. Here's the example here. We use the word implements, and we string them. This is only one. We can go implements comparable, comma, XYZ, comma, ABC, comma, A and G, comma, etc. and so forth. 2 steps to make a class implement an interface. Declare the class intends to implement the given interface by using the implements keyword. And that's this example here. This is what you'll see. More common, you'll see this. You'll see implements. So class employee implements comparable. And then you can string off all of the implements you want. If this were C++, there are no interfaces. Instead, everything's abstract. Well, if you use virtual, you automatically. In fact, there's no such thing as an abstract class. There's virtual. The keyword virtual makes these classes abstract, but in C++, you can inherit from multiple classes. You can go, class employee, and then, inherits from, different syntax, but you can go, colon public, this, comma, this, and you just put them all in there, and you have multiple line inheritance. Java is a single line inheritance, which is kind of weird, but the concept of the interface provides multiple. So it's the same thing as including multiple classes, abstract classes, essentially. So one method is to use the keyword implements on the class line when you create the class, so class employee implements comparable. The other method is to supply the definition for all the methods in the interface. So we have public integer compare to, which is the object itself. Object is the other object, and here we have employee other is equal to employee other object, if this, that. So note, in the comparable interface declaration, the method compare to is public implicitly, but this modifier is omitted, so we don't have public in here in terms of the compare to. Where'd it go? Okay. But the employee class design, you cannot omit the public modifier, otherwise it will assume it is a package accessible. So for package protection purposes, you'd probably want to put it in. You'll see it this way: implements something. It's a lot clearer, actually, to not implement all of the different interface methods, but just to implement the interface in terms of the class declaration. So if you implement the methods that are part of the it's part of the interface, there's no need to have the interface, essentially, because you've implemented the method. If that makes any sense. If a class leaves any method of the interface undefined, the class becomes abstract class and must be declared abstract. So, because it meets the definition of an abstract class. So you have class A that implements class B. Class A must implement all of class B's methods. If not, you go abstract class A implements B. And then you have class C that implements class A, or whatever the abstract one was, and you build an entire hierarchy until you actually have it all implemented. It delays the implementation till later on in the hierarchy. If you're going to override it, don't implement it, delay it. So you do that when you know you're going to override something. And going back to the shape, if I have area and area ends up becoming in a cylinder and a cone and a circle and all these other little shapes that I have, I'm going to delay that area method until the very last object of that particular type, because I'm going to come up with a different value or a different calculation for each one of those shapes that's derived eventually from all this concept of the cylinder or something. So a single class can implement multiple interfaces. Just separate the names by commas, as I mentioned before. Down here at the bottom of the slide, I've got class employee implements comparable, comma, clonable, comma, anything else you want. Lucky for you, you don't have to write any programming assignments that create any implement any interfaces. You're only going to implement interfaces, you're only going to create interfaces when you have a huge project. Instead, what you're going to do is implement interfaces that are already in the language as the base classes. And then we'll see that when we start looking at the data structures, because we have interfaces for everything. And we have, abstract classes for everything. Because if you're going to make it the concept of a stack, why make it for integers or for floats or for doubles when you'd have to have a stack created for every single data type out there that's going to be held in terms of this data structure. Instead, you make an abstract concept of a stack, and then you implement it for, doubles, floats, whatever is going to store in your object types and stuff like that. So it allows you to delay the implementation, but you still have the base concept. So instantiation properties of interfaces are not classes. You can never make an instance of it. You can never make a new operator to instantiate one. So comparable x is going to be equal to new comparable does not work. Will not work. You can still declare okay, here's the interesting thing. So you can still declare interface variables because they're concept based. So you can say comparable x. That's okay, actually. The same way as you said, person P is equal to new employee. It's a reference, so comparable X is a reference to a comparable. It's not an object of a comparable. So the reference is okay. But they must refer to an object of the class that implements the interface the same identical concept as the person P that equaled to a new employee. Well, inside of the employee is a person. So inside of whatever instance of whatever object you create has to implement the interface. If it implements the interface, then it's equal. So if employee implements comparable, then X could be equal to a new employee, no problem. Same concept as the person. It's referenced, which is an abstract person, if you remember, was an abstract class. Same rules in terms of the reference variables apply towards interfaces as well. Lo and behold, you can extend an interface. I don't know anyone who really does this, actually. I mean, unless, well, okay, so if you're building a base hierarchy, you're going to do it. If you're later on, when you're creating an application, from an application perspective, you're going to be using built-in interfaces. If you're creating something that's kind of unique, you know, and you're building the base hierarchy for it, you might extend one interface to another, and you can. You can inherit inherit and extend interfaces from other interfaces. So extending interfaces, which means inheriting them. So interfaces support multiple inheritance as well. So multiple inheritance, so an interface can extend more than one interface. Where classes can only extend one class, and interfaces extend multiple interfaces, just the same way as you can implement multiple interfaces inside of one class. So superclasses, super interfaces, and sub-interfaces exist. As an example here, we have public interface serializable runnable that extends IO, Java IO serializable, comma, runnable, comma, whatever it extends. So and the keyword here is extends, that's inheriting from multiple different interfaces. You can't do that with classes, but you can do that with interfaces. So extending interfaces about constants, constant variables that are inside of there. An extended interface inherits all of the constants from its super interfaces. So you get all of them. You inherit everything. Takes care of super interface inherits more than one constant with the same name, or the sub interface and the super interface contains constants of the same name. You always use the sufficient enough information to refer to the target constants, which means whichever sub interface you're working with will use that associated. So they're hidden, they're not really overridden. So you use that associated constant that's associated with the interface that you're referring to when you refer to the object. And yes, this is a tedious detail. Tedious detail number one. When an interface inherits two or more constants with the same name, when is this ever going to happen to you? Because you'll create interfaces. Will you ever extend multiple interfaces? Depends on how many base classes you'll actually building in your programming career. Most of you will probably be doing application level work. Never probably end up at this level. But here's an example, and the subinterface explicitly uses the super interface name to refer to the constants of the class. And this is using the dot A, so A dot value. So we have interface A and we have interface B. This is actually kind of important because you can do this with classes as well. So although this slide is pertaining to interfaces, you can do this with subclasses that all can. If you've taken and you've reused the same name over again, although you might discover this is kind of confusing when you look at it. It's hidden, it's still there. You can still use value that came from interface A and came from interface B, and interface C extends A and B. Well, which one are you talking about? Well, you can say A.value versus B.value. You can still reference it by its object, which is the same thing you can do with hidden variables of inherited objects as well. So if student had value and person had value and it was overridden, you can say person, I want the P dot value instead of the S dot value. And you can actually get at both values. Terribly confusing to anyone who would ever actually do this. So normally you just want to keep value as value and use something else, use a different name for that variable. Otherwise you've hidden it throughout the hierarchy and you've got hidden values in there that you can access. No sense. And here it is again. Here's the explanation I just gave you actually for hidden. So if a super interface and a sub interface contains two constants with the same name, then the one belonging to the super interface is hidden because you've overridden it. So once you take and create a new definition for it, the previous one is there, but it's not accessible unless you get it through the object reference. Is basically what I just explained to you a few minutes ago. So in the subinterface, you access the subinterface's version constants by directly using its name. It's dot resolution, if you want to use that terminology for it. So you can access the super interface's version constants by the super interface name followed by the dot. So you can say, this is what we just looked at in the previous slide actually, but getting into the concept of the hiding aspect. So outside the super interface and the super interface, you can actually do the same thing. You can use the dots again on it. So you can access both the constants of explicitly given, the interface itself, by going x dot something, y dot something, and the something is the same. So, and you can actually do that with instances of objects too if you wanted to. Not good practice, however, because it's slightly confusing. So, plus, you're kind of defeating, in this particular case, you're sort of defeating the concept. If you do this without interfaces for classes, you're defeating the concept of inheritance. Because inheritance is supposed to take base functionality and overload it, build it, build it, build it, build it. Interfaces, this is a common problem that happens naturally because you're inheriting from multiple interfaces. So there might be an X over here, an X over here, an X over here, and you've included it all. That's when you're going to be doing this. Otherwise, and that's where you have hidden data, or hidden methods actually as well. That's when you're going to use this dot resolution to kind of go, what interface were you referring to? As a classic example, let's say you have two dates. Going back to another example I gave you, you've got the util and you've got SQL packages in there. You're going to use a dot resolution and go, I want the date from SQL versus the date function from util versus the date function from my date or whatever that I've included in there. Happens with interfaces quite naturally. It's hard to avoid the problem. It's easy to avoid the problem with inheritance with classes. You just don't use the same name over and over again. So, all right, tedious detail number 3, and I don't think I have too many more of these left. When a super interface and a subinterface contain two constants with the same name and the class implements the same interface, we've got the situation in which the class inherits the subinterface version constants as its static fields. So their access follows the rule of the class's static field access. So it's just as if it were a class and you're accessing it from the class access level. So inside of the class Z, we can, and outside of the class Z, we can actually access it as if it were static. Well, it's a class. So it comes from class Z, whether it's inside or outside of the class. So it works just like a static field, static data member. All right, I'm not going to go through the rest of this because you're never going to do this, but it's tedious. Extending interfaces about methods. These were the last couple of tedious points I gave you were in terms of data members, repeating data member names, things of that nature. A couple of different problems occur with methods. Obviously, you can have repeated method names. You can have methods that override or overload other methods and interfaces as well. So if a declared method in a sub-interface has the same signature, this is the interesting part. So you can always change the signatures around as well. Signatures mean the number of parameters in the order in which they're set. So if it has the same as the inherited method of the same and also the same return type, which means it's the same, then a new declaration overrides it automatically. So the same rule as works with inherited classes works with inherited or implemented interfaces and multiple interfaces. They override each other. So it's the last one you used, which is the one you're going to get at. So if only the difference is the return type, then you get a compile time error because it can't resolve it. Because this isn't inheritance. This is implementing of interfaces. So you can't use them all. You can only have one. So you're going to get compile time error because it's essentially like a non-object-oriented programming where you've got two methods with the same name. You're going to get two variables with the same name. You're going to well, not variables, but methods are going to give you an issue. So an interface can inherit more than one method with the same signature and the return type. The class can implement different interfaces containing methods with the same signature and the return type as well. Overriding in interfaces has no question of ambiguity. because you've overridden it. Nothing is hidden, it's overridden. So real behavior is ultimately decided by the implementation of the class that's implementing them. So the class that's implementing the multiple interfaces is going to decide which one of the methods with the same name and same signature it decides it's going to implement by referencing the interface. Real issue is whether the single implementation can honor all of the contracts implied by the methods of the different interfaces. So, methods of the same name but different parameter lists are overloaded. Same concept as an inheritance. So unless you'll never run into these situations at all unless you're implementing interfaces from other interfaces and implementing multiple interfaces in the same class, which hardly comes up, really. So why use interfaces? So you're sitting here going, well, what in the world? Why are you even mentioning this to me? Well, here's our interface. In fact, I have this example out on the bhacker.com website. This is a great example for why you're going to do it, and it's just emphasizing the point that I've already told you essentially. You can use multiple implementations in the same concept. If it's the concept you're concerned with, the interfaces provide you the template for the concept and allow you the option to implement what you want out of the concept. So we have the interface shape, and it's shape.java, and they all have the .java extension on them as well. They all look like classes, but some of them are interfaces. The class implementation to this interface is points. So we have a shape that turns into a point, and then we have a point that's a circle, and we have a circle that comes from point, we have cylinder and circle. Anyway, we have all of these different subclasses that are coming out of this one particular interface, and the interface concept was the shape. So we have subclasses that come out of there, circle and cylinder. So the usefulness of the interfaces goes far beyond the simple publishing protocols for other programmers. Any function can have parameters that are of interface types. Any object of the type that implements an interface can be passed as an argument. Long story short, bottom line, it gives you multiple inheritance for classes. Because if you think of the concept of multiple inheritance, you're not including everything. You're just including what you want. Because if you take all of these classes and you inherit them all into one class, are you really going to get the product of the whole of all of the sum of the parts? You're going to get some odd construction that includes a little bit of this, a little bit of this, a little bit of that, all put together. And why go through the issues and problems of implementing everything when you're just going to change the definition in the eventual class that's going to come out of this? And interfaces are sort of like abstract classes, but you can include many of them if you want. So, let's see. Oh, also used for tagging. You'll see the keyword tagging, and this is way above and beyond the scope of this course, so I'm going to kind of skip through the next couple slides because you really don't have to know this for anything. But it's in here only because it is part of Java. But we have the concept of marking, and then we have the concept of object cloning that I mentioned earlier in the lecture. Cloning one object, essentially making multiples of it in terms of multiplicity. The other odd concept, which I've already talked to you about, is called tagging, and which means it uses the is-a. So a person P that equals new employee, there's a tag inside of employee that says he's a person. And the tag is what allows the assignment, even though it's an abstract person. So you can mark, you can include interface. This is why another reason why people use interfaces. You can include interfaces inside of objects that you create to tag it, to make them all compatible. So if you didn't want to create a person, but you wanted to tag an employee and a student to make them compatible with person, you'd include the interface in there, or you'd include an abstract class person in there. Instantly they're all compatible because they're all including the same marking. And the marking is that person, either an interface or an abstract class. And so it's really referred to as a tag or a marking. So the marking or tagging in interface has neither methods nor constants in it. Its only purpose is to allow the instance of to work. So I can say, is this an instance of person? Yep. Is that an instance of person? Yep. We're all people. It's kind of like giving you a special ID card and putting a number on there and you all have the same number. because it's all inside of your implementation. So you're all compatible. So you all get in, or you all have access to something, or you all have something that we needed you for. So that concept is called tagging. Clonable interface is an example of tagging because we've cloned you. We've tagged you with something and then we've cloned that tag across the entire student body so you're all compatible. And so the object clone itself, so a clone method returns a new object whose initial state is a copy of the current state of the object. So basically we can clone and invoke a method to clone on an object, any object. And we've made multiple of the same object, is what that's referring to. And it's essentially the same, actually. It's a copy of it. Subsequent changes to the new clone should not affect the state of the original clone. It's, you've basically just made a copy of it, and then you've changed the copy around. So, 3 factors in writing a clone method. Empty clonable interface can be used. You must implement it to provide a clone method. It's kind of, if you're familiar with C or C++, it's synonymous with the copy constructor, actually. So objects don't have copy constructors in Java, but they have clonable methods. Clonable methods create a copy of the object, which essentially you can fill in the method body using an interface. You can fill in methods into an interface, include the clonable interface, and all of a sudden when you clone the object, just like a copy constructor and concept, all of these things are going to happen. All these things are going to happen automatically. If you're not familiar with C++, don't worry about it. If you don't know what a copy constructor is, don't worry about it. If you do, that makes sense. If not, don't worry about it. You're not going to be tested on clonable. You're not going to be tested on tagging. You're not going to be tested on using multiple interfaces either. This is above and beyond the scope, but I can't say I didn't give you everything. So. Alright, so the clone method implemented by the object itself performs a simple cloning, copying all the fields in this messages. We get a special, and we haven't looked at this yet, but pretty soon we're going to be looking at exception handling. So clone not supported exception actually will be thrown if you have this implemented correctly. So here's an original, here's a copy. They actually take up 2 separate memory locations in the runtime environment. So once you've cloned an object, it really is a clone. It really is a copy. It's not affecting the original object after that. So object provides methods name. The method name clone, which is part of object, and it's run from object, which is inherited in all classes that you create, performs a simple clone, simple copy. So. And I'm not going to go through this, but the shallow and deep copy actually exist in terms of cloning. So way above and beyond. So. Let me skip through. This slide here is actually towards the end. Okay, this is the last slide. It's very good. So this is kind of putting a summary on what I've already kind of mentioned to you, which was not in the slide set, but is now occurring on this last slide here. The reason why I'm using these, implementing these interfaces. Interfaces and abstract classes are generally used together. So why bother introducing 2 concepts? The abstract class comparable. The employee extends comparable, the public interface comparable, employee implements comparable. Well, where are you going to get, multiple? You can't. It's only one in terms of that. So a class can only extend a single abstract class, but it can implement as many interfaces as it wants. So it gives you multiple inheritance, essentially. And it's the same concept. But in other languages, the other object-oriented languages that provide you the ability to extend multiple classes allows you to actually make more error because you can extend behavior you're never going to use. That's implemented, that's included, that you could possibly run, but it's a waste of memory. It's a waste of space. So you might consider this as being a more efficient way of actually implementing the object-oriented concept. Abstract classes can have a partial implementation, protected parts, static methods, and so on. Interfaces are limited to public constants and public methods with no implementations. So we couldn't have one or the other. We can't just have abstract classes and just say, well, we'll just implement, just include multiple abstract classes. Well, and the interface actually just provides you with, because you can implement multiple interfaces, it restricts you to implementing and including only concepts and not implementation. Abstract classes are kind of weird because you can take a full class and just make one method abstract, and so all of a sudden you have an entire abstract class where 90% of the class is actually implemented already. Can't do that with an interface. You can't implement anything on an interface. So you don't have as much flexibility with the interface as you do with the class. So long story short, if you're going to use them, you're probably going to use them together, and it's because you want to achieve multiple inheritance. And you want to implement further down the road concepts that you are just developing at this point. And further down the road, you're going to implement it. So you extend classes and then you implement the interfaces. So I'll leave you with that. Don't be concerned if you don't get the interface concept. We'll see it live on Wednesday with source code examples. So that's all for Java for today.